Good morning, fellow mathematicians. Welcome back to another video. It is finally time, after 2 years and not being as burned out anymore as I was last Christmas season. It's fucking finally time once again for
Papa Flammy's Advent Calendar.
Oh, fucking hell yeah. It's gonna be a blast. Over the course, from the 1st to 24th of December, you are gonna see each and every day a video from my side. This time not only on this channel. If I don't post anything here on a certain day in December, it's gonna be over on my cooking channel or maybe on Flammy's Wood. I'll let you know in my community. Also, during this time, you are gonna get 15% of everything merch related in my Teespring shop using the code self. Not a joke, this is the code. And also you are going to get 10% of everything using the same code over on stemmerch.com on each and every part of the merch over the course of the Advent calendar. So definitely make sure to check it out and support the channel this way. And today we are going to start off on the first day of the Advent calendar with a banger. At least I do hope so. This differential equation, y double prime plus e to the y is equal to 0. And it's going to be an improvised session. This got recommended to me on YouTube. I think this was one of this Michael Patton guy's videos. I haven't watched it, but I'm gonna try to figure it out and see where this gets us. Because I have a certain idea in mind and I hope that it does work. So yeah, try it out for yourself. And now we are going to start with the improvised session. Now, what my idea here is explicitly is this differential equation that we got right here is something of the form y double prime plus f of x is equal to 0. Now this right here is extremely similar to Hooke's law, basically. If we were to multiply everything by a mass m on both sides, then we would get a force out in some kind of way. This is like the same ansatz that you would get when deriving the conservation of energy law. T plus U is equal to the total energy of a system. I have made videos on that in my classical mechanics course here on this channel. Check it out. It's a pretty good course. And the way to go here is to multiply both sides, because this right here would be the acceleration if you interpret it like this. Multiply both sides by the velocity. Because this way you can make use of the product rule. This is my idea here and I hope it does work out. And it should also work out fine with the e to the y. This is at least what I thought of. So I'm going to separate this a tiny little bit. I'm going to separate this a tiny little bit. It really doesn't matter. I can leave it how it is, I suppose. Multiplying both sides by y prime, so the velocity in that regard, we get y prime times y double prime plus y prime e to the y is equal to 0. Now, actually, it's just a matter of a factor, but it would be nice to multiply it by 2, I guess, because 2 is equal to is not equal to 0. Because if you take a look at this front part, and this is the main idea here, if you take a close look at that part right here, this is very similar to differentiating with respect to x, because y is a function with respect to x, and y prime and y double prime obviously too, of y prime times y prime. If you differentiate this, you gotta make use of the product rule. That's the main idea here, to get yourself basically a differential out that you can just cancel out using integration. And then you are going to get y prime, y double prime, plus y double prime, y prime, which is the same as 2 times y prime, y double prime, which is what we got here. And y prime times y prime is y prime squared. So this front part right here is nothing other than the differential in x of y prime squared. And kind of the same thing with the exponential right here. Is so too with the del x, because this also holds for any function that you got right here. That's the magic about it. It's just a chain rule basically. And the cool thing about differentiating the exponential function is you're going to preserve the exponential function, and also the inner derivative is going to be y prime. So this part right here is the same as del x of e to the y. And yeah, now we got ourselves an equation. You can also bring this part to the right-hand side and then basically cancel out the differentials using integration. What you're gonna get is we get del x y prime squared is equal to, bring this to the other side, -2 is a constant. We can drag it to the front of the differential operator, del x e to the y. And now integrating both sides with respect to x, this and that is gonna cancel out, you can say. E to the y is, no, it really doesn't matter because, well, we are integrating something that we differentiate, okay? So we're just gonna end up with the function in here in and of itself. Same thing here, you could say, okay? But we're gonna end up with constants on both sides. We can subtract this one constant to the other side and absorb it into the other one, giving us overall for now that y prime squared is equal to -2 e to the y plus some arbitrary constant c. And yeah, this should work out. This is actually separable. And this is where I wanted to go at. And this is the same ansatz that you use for conservation of energy. As I said before, this right here would be the, so we got the velocity squared, multiply this by m/2, you are going to get yourself the kinetic energy out, and this right here could be any potential energy. We don't know what the potential energy is, but it could be any potential energy. And if we don't have any dissipation going on, so no thermal energy, then we get the kinetic plus the potential energy is equal to some constant c, which would be total energy of the system. And that's a very beautiful approach, and I just love this classical mechanics derivation, which also holds in quantum mechanics, and it's just absolutely beautiful. I should do more physics videos here on this channel. Spoiler alert, there's gonna come one over the weekend. It's gonna be a fun one. But nonetheless, now we can take the square root on both sides, giving us that y prime is equal to plus minus the square root of, let's bring this in order, I hate when the negative sign is at the front, c minus 2 e to the y. And since that is a function with respect to y on that side, we want to bring it to the other side to separate it. We are going to divide both sides by it, giving us that 1 divided by plus minus the square root of c minus 2 e to the y times dy dx is equal to 1. And now we can simply integrate both sides with respect to x, obviously. Yeah, 1 is going to be absorbed in the integral here, dx. Dx and 1 over dx is going to cancel out. You could say, okay, take a look at my differential equation playlist. I'm talking about this there, but it just is what it is. If you differentiate this differential right here and integrate it with respect to x, it's going to cancel out, basically. And then we get this integral, which looks yucky, 1 over the root of an exponential. This doesn't look trivial. We'll see about that. I think that's the hardest part of the whole thing. And integrating dx, the differential 1 operator, is just going to be x plus some arbitrary constant kappa. Obviously, we get two constants out because it's a second order differential equation. Okay. The plus minus can go to the front. I don't care about that right now. You can also bring it to the other side. Really doesn't matter. And now we are just going to deal with this integral right here. Let us see where this gets us. Okay, so we get the integral of 1, so dy divided by square root of c minus 2 e to the y. Yeah, that's right. Okay, that exponential is bugging me. I could probably just substitute the whole thing here. But then I would get a logarithm out after substitution, right? Probably, because if I were to solve this for the other variable, for implicit differentiation, then probably getting a logarithm. Not certain about it, but with the additional, I'm just going to get rid of the e to the y at first. So let's start with the substitution. Let e to the y be equal to, I don't know, a. I think I've never done this before. This is ugly. Should you use a as a new variable in an integral? That sucks, I suppose. That means that e to the y dy is equal to dA. Dividing both sides by e to the y gives us dA over a here. And our integral is now dA divided by a times the square root of c minus 2a. Okay, so we got rid of the e to the y. And it would have probably been the same if I just substituted everything for a new variable. But I feel safer now at least, because this is not going to result in anything ugly, I suppose. I'm just going to substitute the whole thing such that we can get rid of the square root in some kind of way at some point at least. Let c minus 2a be equal to, after a comes b, I suppose, b. That means that we need to substitute a in. So let's solve for a, 2a on the other side, b on the other side. So a is equal to c minus b divided by 2. And differentiating this part right here, it's also going to get us that negative 2dA is equal to dB. Yeah, that also looks ugly. Database. Who wants this as his new differential one form? Dividing both sides by negative 2 gives us this. Okay, let's sub it in. We are going to get, so negative 1/2 is a constant. We can bring it to the front. Doesn't matter, linearity of the integral. Then we get dB, obviously, up here. Then we get divided by a, and a is c minus b divided by 2. So, oh, that's actually nice. 2 gets to the front, reciprocal, c minus b here, times the square root, and parentheses, obviously, square root of b. 2 and 1/2 is going to cancel out. Meaning our plus minus later, we shall not forget this, or maybe it cancels out at some point, this negative, it's going to turn into a minus plus, even though it probably doesn't matter for the family of solutions to the differential equation, I suppose, because we get both branches. But we're going to be rigorous here, or something of that sort. Says the person who cancels out 1 over dx with dx, or even says something like 1 over dx. Oh my fucking lord. Okay, so we got this now. Let's clean this up a tiny little bit. And if we now get rid of the square root of b, substituting this for another variable, we are just going to get, it's the new variable squared over here then. And with the square root of b, this differentiated is just, this should actually turn out nicely, because in a normal case we should get the new variable up here, and also after substituting this variable here. At least this is what I'm seeing in my head. So I don't want to use c, let's use t. T is my most favorite variable ever. Let t be equal to the square root of b. We need to substitute b later, and this also makes solving after implicit differentiation a bit better. That means t squared is equal to b, and differentiating this implicitly gives us that 2t dt is equal to dB yet again. If we plug this in, we get negative the integral. That is not a nice one, no. I don't want you here on my blackboard. That's a nice one. That's a nice integral. dB is 2t. We gotta bring 2 to the front. Let's clean everything up. dt here. Also we get c minus t squared. And we get a t down here. Oh, this is so nice. I did not expect it. I thought that this integral would fuck me in the ass here. But I'm always getting kind of lucky with those square root integrals on the improvised sessions. See the square root of the tangent and the like. Those are fun. Check out the whole playlist. Did a bunch of those improvised sessions already. So what we overall got is now negative 2 times the integral of dt divided by c minus t squared. This just screams for partial fractions. But I don't like how it looks right now with the c. Gotta factor out the c on both terms. So we get negative 2 divided by c. times dt divided by 1 minus t squared divided by c. We could in fact just once again substitute something. So substitute this right here. But I actually got a different idea. So we got to bring it into the form of something squared once again in its entirety. So this is a common trick when you use, for example, or if you want to use the integral of the inverse tangent, for example, that would be the integral of 1 divided by 1 plus blah 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 squared. Then you would say that c is the same as the square root of c squared. Then you can drag the square to the outside using exponentiation rules. And now you can substitute for a new variable. Let s be equal to t divided by square root of c. Multiplying both sides by square root of c gives us that square root of c ds is equal to dt. Then we get negative 2 times the square root of c divided by c. Square root of c divided by c is just 1 over square root of c. So negative 2 divided by the square root of c times the integral of dt divided by 1 minus s squared. No, s ds, not dt, right? Okay. And this looks like the inverse tangent integral. But it's not, because it got a negative sign here. I'm gonna take a gamble here that this integral results probably, I could do partial fractions, I suppose. Then we would get something like logarithms for partial fractions. So this right here is 1 minus s times 1 plus s. So we get something blah 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 over 1 minus s, something over 1 plus s. So we get a 1. Does this work? Then we get s and s are gonna cancel out. But then we get a 2 up here, right? 1 plus 1. So the whole thing would be multiplied by 1/2, I guess. Then that would probably work out. And then you can just get yourself logarithms. And the inverse hyperbolic functions as well as the inverse trigonometric functions are also with respect to logarithms. It probably is the inverse hyperbolic tangent because we got the relationship that tang squared plus hyperbolic secant squared is equal to 1. So if we subtract the tang on both sides, we got 1 minus something squared. And implicitly differentiating this is probably going to get you that this right here is going to be the differential of the inverse tangent. Okay, I made several videos on that, but I can't remember if I ever derived it. I'm going to go with the idea that this could either be something, the difference or the addition of two logarithms of 1 minus s and 1 plus s, or it could be a negative 2 divided by c times the inverse hyperbolic tangent of, in our case, s. Oh goodness, so many substitutions. S is t divided by square root of c. T is the same as square root of b. B is the same as c minus 2a. This is going to get wacky. Oh my goodness. Inverse hyperbolic tangent of... that's the square root in its entirety. So we're going to bring those together. C minus 2a divided by c. And a is... If I would have used c, that would have been a real clusterfuck with the c's up here. And a is e to the y. Our original boy up here, c minus 2 e to the y. And now we are back. plus some arbitrary constant, which we can absorb in our kappa. Meaning we are not done yet, right? Because we... this right here is the same as x plus kappa. Also, we got the plus minus down here. As mentioned before, we shall not forget this. Turning this into minus plus. And this is where we are at right now. And since it's a differential equation and we want to get a solution out, we need to solve for y. This shouldn't be hard, but it's a hassle, I suppose. Multiplying both sides by plus minus square root of c divided by 2 gives us plus minus square root of c divided by 2 times x plus kappa. Okay, so we got rid of that. Using the hyperbolic tangent on both sides, we are gonna get that the square root of c minus 2 e to the y divided by c is equal to the hyperbolic tangent of square root of c divided by 2 with plus minus at the front, x plus kappa. And now we can square this bit on both sides. I'm not going to erase anything on this blackboard now. And now we can solve for the rest. Multiplying both sides by c times the hyperbolic tangent squared. Then adding 2 e to the y on both sides and subtracting this bitch boy. Then we get c as a common factor. I need to save space. We can factor this out then. Then we also divide by 2, giving us c over 2 as a common factor and 1 minus the hyperbolic tangent squared. Let me gather this and I hope shit is correct. Then we get e to the y is equal to, what did I say just now? Give me a second. So we get c over 2 as a common factor. And here we get 1 minus the hyperbolic tangent squared of, this looks wrong as fuck, but it's probably right. Differential equations most of the time are not nice. X plus kappa. And now, taking the natural log on both sides, we are done. That means that y of x, the solution to our original differential equation, which looks extremely harmless, because we all know exponential function differentiated is easy, it's just itself, but no, the problem is with the y up here instead of an x. We are gonna get that y of x is equal to the natural log of c divided by 2 times 1 minus the hyperbolic tangent squared plus minus the square root of c divided by 2 times x plus kappa. And that's it. And I hope you did enjoy the first episode of Papa Flammy's Advent Calendar. And here's the solution by Wolfram Alpha, and I hope it's right that I didn't waste my time here. I think on all those improvised sessions, I only had 2 or 3 sessions where my final answer was not right or off by a constant, most of the time a negative sign that I lost in between. But we did it very carefully. I hope we did well. And if you did enjoy what you've seen today, definitely make sure to subscribe to stay updated for the rest of the Advent Calendar. And also don't forget to check out NP Cooking, my NPC channel, and also Flammy's Wood. Gonna upload over there at some point in time, probably this weekend, 1 video too. So stay tuned for that. Especially the cooking videos are a lot of fun. You should check those out, even if you're not into cooking, you filthy boy. And yeah, there's not much more to say. I'm excited for this year, and I hope you are too. I wish you guys a flammable day. See ya!